Okay, welcome back everyone. In this next segment, we're going to take a few minutes to look at how we can use Newton's second law, F equals ma, to solve some problems. So I want to provide you sort of with a strategy, and we want to do this by kind of working through problems in a systematic fashion. So it just kind of makes sense that the tougher the problem is, the more important it is to have a procedure to follow. So you don't have to follow this, but this is just a suggestion. The first thing that we'd want to do is figure out what object or objects we're analyzing. And we're going to select a reference frame to analyze this in. And it's key that we don't want this reference frame to be accelerating, because then Newton's laws of motion don't work right. We're going to draw a free body diagram which isolates the forces on one object. And then we're going to set up F equals ma for each object in each dimension. So typically for one object, we'll be doing x and y, but if we have more than one object, then you can see that we're going to have a system of a lot of equations. Use kinematics or calculus to obtain the acceleration, and we'll substitute what we know, and we'll calculate what we need to. So here's an example. Okay, a 5-gram bullet leaves the muzzle of a rifle with a speed of 320 meters per second. It's accelerated while it travels down the barrel. Assuming constant acceleration and no friction, what's the force on the bullet? So the first thing we're going to do is identify the object to be analyzed, and that's the bullet. The reference frame is just going to be our reference frame, which is stationary, and we want to draw forces acting on it. So the bullet is just going to have the force of the gas. Okay? Now we want to set up F equals ma for each dimension, and we're going to ignore what happens with the force of gravity, because if I have the barrel of the gun here, it's going to be in there for such a short time period that we're not going to worry about it. So we go directly to our step 4, which is to set up the sum of the forces equal to mass times acceleration. And in this case, we just have F gas equals ma. Okay, now we're trying to calculate the force, so we're going to need to use kinematics to get the acceleration. Okay, so F is what we want, but A is our sort of intermediate goal. And in order to do this, we can note that we have a distance of 0.820 meters, and we have a final velocity of 320 meters per second, and we would assume that we have an initial velocity of 0. And so we could take that information and set up a forgotten equation. And so that's just going to look like v final squared equals v initial squared plus 2a delta d. So this is our delta d here. And so v initial is 0, and we want to solve this for acceleration. It'll just be v final squared over 2 delta d. And I've calculated this out to be about 62,440. I'll just round it, 62,400 meters per second squared. And so we could take that acceleration and plop that into here so that the force of the gas is equal to the mass, which is 0.005 kilograms times 62,400 meters per second squared. And that's going to get us just about 310 newtons of force. Okay. Now it's really important when you do this to make sure that you put mass into kilograms instead of grams. Here's another example problem. Now we have a 3 kilogram mass that has an acceleration which is given, and we want to find the resultant force and its magnitude. So we start with the fact that F net equals ma. And in this case, we can just jump straight to the math. We don't really need to set up and draw the system because the acceleration is given. So that means that the force is just going to be 7.5 I hat plus 12.3 J hat newtons. So I'm just multiplying by 3. And then to find, so that's the actual force. If I want the magnitude of that, then I could just take the square root of the components. And that's going to get me something that's pretty close to 13. It's actually about 14.4 newtons. Okay? Alright, so in the next video we're going to start looking at different types of forces, including the normal force and tension and friction, and see how that affects our setup.